three electric power plants with the respective capacities of 20, 40, and 30 million kilowatt hours supply electricity to three cities. The maximum demands at the three cities are estimated as 30, 35, and 25 million kilowatt hour respectively. The price in birr per million kilowatt hour at the three cities is given in the table below. This is the cost matrix for the distribution of electricity from the three plants to the three cities. During the month of June, there is a 20% increase in demand at each of the three cities, which can be met by purchase of electricity from another network at a premium rate of 1000 birr per million kilowatt hour. The network is not linked to CT1. The utility company wishes to determine the most economical plan for the distribution and purchase of additional energy. Question number 1. Determine the initial feasible solution by using least cost cell method and calculate the resultant total cost. Question number 2. Determine the cost of additional power purchased by each of the two cities. The first step for solving problems of this type is constructing transportation tableau. So let's start to construct the tableau by using the given cost matrix. The given cost matrix doesn't include power purchase from external network. Rather, it includes only the three power plants. Hence, we have to add the fourth row in the tableau because sources are designated by rows. As it is mentioned in the problem, the external source is not linked to CT1. Thus, there is no unit cost to be mentioned in the external source to CT1 route. Unit cost for the transport of electricity from external source to each of CT2 and CT3 is given as 1000 birr. The tableau doesn't include supply from each source and demand of each city. The 20% increment raises the estimated 30, 35, and 25 million kilowatt hour to 36, 42, and 30 million kilowatt hour respectively. The increased demand can simply be calculated by adding the original demand and its 20%. Demand had to be expressed at the bottom of each column corresponding to the respective city. Thus, CT1 demand is 36, CT2 demand is 42, and CT3 demand is 30, each in million kilowatt hour. Supply has to be expressed at the right-hand margin of the tableau corresponding to each source. Supply from plant 1 is 20 million kilowatt hour, from plant 2 is 40 million kilowatt hour, and that of from plant 3 is 30 million kilowatt hour. The external network is needed for the increased demand, which can be calculated as a difference between the total demand and total supply. Total demand is equal to 36 plus 42 plus 30, which is equal to 108 million kilowatt hour. Total supply is equal to 20 plus 40 plus 30, which is equal to 90 million kilowatt hour. Total demand minus total supply is equal to 108 minus 90, which is equal to 18 million kilowatt hour. This is a complete transportation tableau, which is used to set initial feasible solution. We have some steps to be followed for setting initial feasible solution by using least cost cell method. So let's set the feasible solution by following the steps. The first step, select a cell with minimum cost and then allocate as much flow as possible to that minimum cost cell by choosing the smaller one from the corresponding demand and supply. Among the given unit costs, the least cost is 300 birr. Supply corresponding to this cell is 40 and demand corresponding to it is 36. 36, that is the smaller one from the two, has to be allocated to the selected least cost cell. Step 2, reduce row supply and column demand by the amount allocated to the selected least cost cell. Deducting the allocated 36 from the corresponding demand and supply reduces the demand from 36 to 0 and supply from 40 to 4. The rule after this deduction is that if all supply is consumed, reduce it to 0 and eliminate the corresponding row from further consideration by drawing a line through it. Plant 2 supply is not reduced to 0, rather 4 million kilowatt hour is left unused. The other rule is that if all demand is fulfilled, reduce it to 0 and eliminate the corresponding column from further consideration by drawing a line through it. CT1 demand is fulfilled, hence column 1 has to be crossed out by drawing a line through it. Step 3, look at the uncrossed out cells to identify the next least cost, and then continue with step 1 for all unlined rows and columns until all demand is satisfied and all supply is consumed. We have to continue our allocation to the 8 undeleted cells until CT2 and CT3 demands are fulfilled and all supplies are consumed. The next least cost cell is 320 birr. From the corresponding demand and supply, the smaller one, that's 4, has to be allocated to this cell. Subtracting the allocated 4 from the corresponding demand and supply reduces plant to supply to 0 and CT to demand to 38. Row 2 has to be deleted because all plant to supply is consumed. 400 birr is the next least unit cost. Demand corresponding to this cell is 30 and supply corresponding to it is 20. 20 is less than 30. Thus, the amount that has to be allocated to this cell is 20. Allocation of 20 to this cell reduces the supply to 0 and demand to 10. Plant 1 supply is reduced to 0, hence row 1 has to be crossed out. At this stage, we have 4 uncrossed out cells. 450 birr is the least cost among these uncrossed out unit costs. Demand corresponding to this cell is 10 and supply is 30. The less one, that is 10, has to be allocated to this cell. Deducting the allocated 10 reduces the demand from 10 to 0 and the supply from 30 to 20. Column 3 has to be deleted because CT3 demand is fulfilled. From the remaining 2 undeleted cells, 480 is the smaller unit cost. Supply corresponding to this cell is 20 and demand corresponding to it is 38. The amount allocated to this cell is 20. Subtracting the allocated 20 reduces plant 3 supply to 0 and CT to demand to 18. Row 3 has to be deleted because plant 3 supply is completely consumed. The only active cell at this stage is plant 4 to CT2 root. Demand corresponding to this cell is 18 and supply corresponding to this cell is also 18. Allocating 18 to this cell reduces both demand and supply to 0. At this stage, all demand and supply are reduced to 0. In other words, this is the initial feasible solution obtained by using least cost cell method. Resulted total cost is equal to occupied cell in column 1, that's 36 times 300, plus occupied cell in column 2, that's 4 times 320, plus the second occupied cell in column 2, that is 20 times 480, plus the third occupied cell in column 2, 18 times 1000, plus occupied cell in column 3, 20 times 400, plus the second occupied cell in column 3, that's 10 times 450, which is equal to 36 times 300 is 10,800, plus 4 times 320 is 1,280, plus 20 times 480 is 9,600, plus 18 times 1,000 is 18,000, plus 20 times 400 is 8,000, plus 10 times 450 is 4,500. The sum of these numbers gives 50,180 birr. This same problem was solved by using northwest corner cell method, and its total cost is 56,520 birr. The less transportation cost obtained by using least cost cell method is an attestation that least cost cell method yields better initial feasible solutions than northwest corner cell method. In some cases, especially when the least unit costs are concentrated on the diagonal of the cost matrix, the northwest corner cell method can yield better initial feasible solutions than the least cost cell method. But in the majority of cases, the least cost method yields better initial feasible solution than the northwest corner cell method because the allocation starts from the least unit cost. Only CT2 purchases electricity from external network at a premium rate of 1,000 birr per million kilowatt hour. So the cost of additional power purchase by CT2 is equal to 18 times 1,000, that is 18,000 birr. Thank you for your attention. Have a nice time.